Welcome. My name is Chuck Ridgway. I'm the Automation Technology Manager here at Horner. Thank you for joining us again for another live stream. This week, after a week of looking at micro OCS wiring, this week we're back to another Seascape programming topic, hopefully one that you'll find informational. This week's topic is using structures with variable-based advanced ladder logic. So joining me again this week is Mr. Casey Gardner. How are we doing today, Casey?
I'm good.
It's going terrific. Hey, so this week it's all about helping our customers who are transitioning from register-based ladder logic over to variable-based ladder logic. So we're trying to give them more tools in their toolbox, more information on the advantages of variable-based programming. And this week, structures is the topic.
Yeah, we've actually had structures, I think, in Seascape for a little while, but it's not something we really focused or highlighted on for quite a while, probably until about last year with Service Pack 3's release, where we definitely added the like timer counters and PID structures built into the variable lists already for you. So it's definitely a powerful tool that you can do a lot with, and I think we've got a lot of good stuff you covered.
Absolutely. And I know with Service Pack 4, we took some feedback from Service Pack 3, which again was the first release last year where we really started to emphasize the variable-based programming. And I've found, at least with Service Pack 4, as I use the variable-based advanced ladder, it's just gotten better and better and easier. So looking forward to a good topic today, like you said. Casey will be manning the chat, so if you have any questions, feel free to chat those. And then at the end of the session today, I'll be bringing Casey back in, and then he'll be reviewing any comments or questions that came up during the program. Okay, let's go ahead and get started. Using structures with variable-based advanced ladder logic in the Horner OCS. So today's topic, what is a structure? We're going to give you some examples of structures to help you visualize what they are and how you can use them. We're going to talk about a few of the built-in structures that come pre-configured in Seascape, namely for timers and counters and PID. We're going to talk about the advantages of structures, and there are several things that can really make your life better as you do advanced ladder programming by taking advantage of that feature. We'll also cover some of the limitations of structures and how you can overcome those. And then we'll also spend, a good part of our presentation, really, probably the last 20 minutes anyway, on a full demonstration. And really the first part of the presentation should only be about 10 minutes. So let's get going. Okay, so what is a structure? So a structure is a feature that's available in our Seascape variable-based logic languages. So that means variable-based advanced ladder, as well as our IEC 61131 logic editor. Structures are also sometimes called data structures, and what they are is a meaningful group of data that is used as a complex variable type. Each element in the structure, sometimes called a field, is individually named and typed. Let's start looking at an example. So let's say we have an application where we've got a large number of motors that we need to control. And each motor has a common set of parameters that are associated with it, such as current, voltage, horsepower, RPM. It needs a start signal, a stop signal. There's fault indication. So these are just examples of different sets of data that is common to all the motors. So using a structure is one way that we can really make our life easier and really keep the application more organized. So in this example, let's say we create a structure and we name the structure motor. And then within this structure, which is again like a group of variables, we add different fields to that structure with a meaningful name, and then we type that individual field. So for current, we name it current, because that makes sense, right? And we assign it the type of real, if that's what we're looking at from a data standpoint. Voltage, which might be typed as an unsigned integer. Horsepower, which could be another real variable. RPM, which might be another unsigned integer. And then we might have some Boolean-based elements, such as start, stop, and fault. And there could be others. This is just an example. So once we create this structure called motor, with all these different fields and different types for the individual fields, we really haven't added a variable yet in our program. All we've done is created the format for the variable. Okay? So our next step is going to be to actually create a variable that takes advantage of the structure. So in that next step, let's create a new variable, which we will call main motor. So as I said at the beginning, we may have a whole bunch of motors that we need to control in this application. Each of those motors is going to have a name, and the variable name for each of those motors is going to be reflective of that motor. So in this case, we're starting with main_motor as the variable name. And then when we assign it a data type, we don't say integer or real or floating point. What we do is we assign it a type of motor, which is the structure we just created. Now, for that main motor, we have access to all those different parameters, which can be seen as kind of subvariables underneath main motor. So to access the variable that refers to the current in the motor, we simply access main_motor dot current. That's called dot notation, and that's what's used in structures. And then we go on down the line. For voltage, it's main_motor dot voltage, and we access that variable as an unsigned integer because that's how it was typed when the structure was created. And then again, we go on down the line, down to the bottom where we have main_motor dot fault, which is one of our Boolean variables that are associated with main_motor because it is defined as of the type motor. Now, in addition to regular non-dimensioned variables, you can also use structures with arrayed variables. Okay, so remember, arrayed variables are variables that would have multiple members with basically a sub in parentheses. Okay, so if we create a arrayed variable called pump motor that was dimensioned to 10, then we would have pump motor sub 0 through pump motor sub 9, for instance. And if we assign that pump motor arrayed variable to the type motor, now we have additional ability to not only specify each of the elements within pump motor, but for each of the 10 different instances of the pump motor arrayed variable. So this can get really powerful really quickly, as you can see. Okay, now let's talk about a couple of the built-in structures in Seascape before I fire up Seascape and we get to the demonstration portion of the program today. So we've taken advantage of structures in Seascape by pre-configuring a structure to take care of 16-bit timers and counters and 32-bit timers and counters. And each of those have fields associated with it. Okay, if you're talking about a 16-bit timer counter, now you're talking about an accumulator field, ACC, which is either a uint for 16-bit or it's a double int for 32-bit. That varies depending on which of the structures you choose. And then you have a flags field, which is an unsigned integer, but really there's only 2 bits in the flags integer that really matter. The 15th bit says that the timer is active, and the 16th bit says that the timer or the counter is done. Okay, it's reached its preset value. So in our example, we could select a 16-bit timer, and then we could name it run_timer, and we could effectively, when we assign that variable to the timer, we have to make sure it's of the type timer counter 16. And if we do it on the fly, like you'll see me do it here in a minute, it just kind of happens automatically. Now, in your program, elsewhere, if you want to access the accumulator, you can access that from run_timer.acc. And that's an unsigned integer if you're talking about a 16-bit timer. If it's a 32-bit timer, it would be a double integer, of course. Now, if you want to access the active bit, then you can effectively access run_timer.flags, but then you have to add an extra dot. Dot 15 for the 15th bit, that's the active bit. And then for the done bit, you're going to access it as run_timer.flags.16. Okay, and of course the 15th and 16th bits are Boolean. All right, so that's built-in structures related to timers and counters. And this was basically a request that was made as we were preparing for Service Pack 3. we had requests from the field saying, hey, why don't you take advantage of structures so that when customers add timers or counters to their program, it just makes it a lot simpler. And so we went ahead and did that. Now, in addition to using structures pre-configured in Seascape for timers and counters, we've done the same thing for the PID instruction. Now, some of you who've used PID before know that every PID instruction has effectively a list of 16 variables that are assigned internally to that PID instruction. And they range from things such as your sample period, to your tuning parameters, to your cycle time if you're talking about a PWM type PID loop. Those are the parameters that are assigned to each PID instruction internally. And to make that easier to use, we have created, predefined if you will, in Seascape, a PID structure type that names and allows you to easily access all those variables. So you can create one variable, and let's say it's called oven underscore temp or something like that, because you're going to be controlling the oven temp from a PID loop, for instance. You create that one variable, and then all the different parameters are accessible with a dot at the end of the oven underscore temp variable name. So that makes things really straightforward and especially easy to keep you organized. Now, and that's some of the primary advantages of structures. It reduces programming errors. Okay, you don't accidentally pick the wrong variable. You know, let's face it, when we do a control program, in the end we may have hundreds and hundreds of variables. So having them named properly and organized properly is half the battle, making sure that we pick the right variable for the right function. So it definitely, the use of structures definitely does reduce programming errors. It improves your organization, makes your code much more readable, and it enforces consistency. So those are all really positive things when it comes to designing really well-written code. Now, there are some limitations of structures, all right, and let's talk about those here. First of all, we do not allow nested structures. So if you define a variable whose data type is a structure, none of the elements of that structure can also be of data type structure themselves. When you define a structure, every field, every element you add has to have a data type, but that data type cannot be another structure. So we do not allow nesting of structures. Another thing that you can't do directly from a structured variable is directly map it to a real-world variable or real-world memory location in the OCS. Okay, so as an example, let's say we've got a variable we're calling start underscore PB for start push button. If that's not an arrayed variable, it's just a regular old Boolean variable that we create, we do have the ability from within the variable creation tool in the variable window, we do have the ability to directly map that to %i5, which might be where it is physically connected, okay, or needs to be physically connected. So that mapping relationship has to occur at some point. With a regular old variable, you can do that in the Seascape variable window if you choose, okay? Now, if you've got an arrayed variable, such as main underscore motor dot start, an arrayed variable does not have the ability to be directly mapped within the variable window itself to map it to a real-world I/O point. However, a simple ladder rung can be created that accomplishes the same thing, and actually it can help you follow some really good programming technique in the process of doing that, and we're going to illustrate that as part of our demonstration. Okay, let's get to it. That's enough talking about structures. Let's go ahead and take a look at how they work. Okay, let's go ahead and fire up Seascape. And what I have here is pretty much a blank slate. All right, so I don't have anything pre-configured here. This is just pretty much a new variable-based program that I've opened in Seascape. All right. All right, let's go ahead and create a new structure based around the one that I talked about during the previous part of the presentation. So here are the three that are already established, pre-configured by Seascape. PID, which has all of those PID parameters pre-baked in, timer counter 16, and timer counter 32. But we want to add one of our own, and let's do the one for that motor. Okay, so I'm going to go ahead and highlight retain variables, right click and select Add Structure. I need to right click again and select Rename Structure, and let's go ahead and call it Motor. I can also add a comment here, all the parameters associated with the motors. All right, I'll hit OK. So now we've defined at least the name of the structure. Let's highlight it and right click and say Add Variable. And as we add additional variables, we can just use the Insert key, as you see. That'll be easier and faster. Okay, the first one I want to add is current. Okay, and that is a real variable. All right, I'll hit the Insert button to add the next one. Voltage. We're going to make that one an unsigned integer. Okay, again, hitting the Insert button. Now for horsepower, another real variable. Insert for RPM. You get the drift here. This is a pretty straightforward process. We'll make this one a unsigned integer. This time I clicked instead of using the tab key. All right, another insert. Now we've gotten to all of our Boolean variables. So let's type those in. Start, which is a Boolean variable, stop, which is another Boolean variable, and fault, which is another Boolean variable. Okay, so we have now successfully created a structure called motor. Here are all the different elements or fields within the motor structure. They're all kind of variables in their own right with the appropriate type for each of the elements here. Okay, but we really haven't created a variable per se. We've just created a new type called motor. Okay, and it happens to be a structure. So to actually take advantage of this structure, we need to create a variable that utilizes it. So I'm going to go up here under Retain Variables, right click, and say Insert Variable or Add Variable. Okay, and let's go ahead and name that as, let's make it pump motor. Okay. Now, instead of selecting, Boolean or real or unsigned integer, we're going to look at the list and we're going to scroll down a little ways below the regular data types, and there are our structured data types listed. Let's go ahead and add motor here, or select motor. Okay, so now we have a variable we've created called pump_motor that will have access to all of these different subvariables, if you will. Okay? All right, so let's go ahead and do something like we often do here with our live streams. Let's just build a simple start-stop circuit that utilizes some of the members of this structure for the pump motor variable. All right, so I'll start with adding a normally open contact. We'll use that as our start. Now, if I want to select a structured variable, I can either just type it in, or I can hit the Browse button here. I'm going to go ahead and do that. So there's pump motor, and I want the start element. I double click here. You can see it filled it in as pump_motor.start. Okay, so I've dropped my contact there. Let's right click and hit New Rung. Time for the stop function. Normally close contact. This one I'll go ahead and type in as pump_motor.stop. Okay. All right, now the next thing is I'm going to need a run contact for this motor. Now if you'll notice, I never created a run contact as part of the structure, and I don't have to. I could just make it a regular old coil tied to a regular old variable, but I think it's probably a good idea. Just about every motor is going to have a run contact tied to a motor starter. So let's go ahead and add that to the structure. So I can go ahead back here, highlight it, hit the Insert button again, and I can type run. Okay, so now I've created another element, or I've added another element to the motor structure, and I can take advantage of that now. So now I can go over here, and let's just go ahead and make that pump motor.run. Away we go. That means that we've got now the ability to make that our seal contact around the start. All right. Again, pretty straightforward here. Pump motor.run. Okay. All right, so we've created a simple start-stop circuit taking advantage of variables that we have created that are all part of a structure, or they're typed as a structure. So that, as you can see, when you look at this logic, it makes the logic very well documented, very logical, right? Very well organized. When I start working on a different motor, it's going to be very easy to select the right variables for my application. Okay, now let's say, for instance, let's say that this stop button is coming from a real world input, which would be pretty common, right? Most of the time when you have a stop button, it's a physical stop button. You might have one on the screen, but then you probably also have a physical stop button as well. Well, as I mentioned in the presentation, there's no way to necessarily, within the variable tool, the variable window, to directly map that as a to a real world input. Let me show you how you would do it for just a plain old variable. Okay, so let's say that I want to create just a plain old variable and map that to %i5. All right, so I'm going to right click under global variable, hit add variable, and again, this is not a structured variable, this is a plain old variable. I'm going to call it stop push button. Boolean is fine, but I'm going to go ahead here under the memory location, all right, and I'm going to map it, let's say, to i7. So I can type in %i7 and away we go. All right, so that's really what you have the option of doing with a regular old variable. Well, there's no way of doing that with a structured variable. Okay, so how would we do that instead? Well, there's actually a pretty good approach that you can use, which is actually a good programming technique. Let me show you that right now. So what you can do actually is, this is our main routine. All right, and over time, as we develop a application, you're going to end up with a whole bunch of different sections of ladder for doing whatever portion of machine control that you want to do on that portion of the machine. It's just good practice. Well, it's also good practice at the very beginning, maybe one of your very first routines, to have a routine which maps all your real world inputs to internal variables. That way later on, if you ever need to change your memory map because your inputs and outputs change, you have the ability to do that. Now generally, you want this input routine to be one of the very first ones that you do. So I'm going to go ahead and move it up in order. So now I've got an input routine, and then my main logic where I solve all my logic. And again, as this program develops, I could have a whole bunch of sections of logic. And then I'm going to go ahead and add another section as well at the end. Okay, and we'll call that outputs, which again is going to allow me to map internal variables that need to be mapped to real world outputs. It's going to allow me to put that information here. Okay, so how are we going to do this? All right, so what I want to do is I want to map the real world input to pump motor stop. And I want to do that in the input section. I'm just going to do that with a simple rung of logic. So I'll drop down here. I'll drop down input 5. So real world input 5. Now, before I show you this, let's go back and review how we might, in ladder, map to real world input 5. At the very beginning of the global variables, which is pre-established in Seascape, you'll see we have, for the real world I/O types of AI, AQ, I, and Q, we have predefined variable arrays named AI, AQ, I, and Q, dimension for the size of number of AI, AQ, I, and Qs that are available. We have those dimensioned arrays that are there. So input 1, %i1 corresponds to I sub 0, because remember, arrays are 0 based. %i2 is going to correspond to I sub 1, all the way up to %i2048 is going to correspond to I sub 2047. So if I want to put a contact here that references the real world I/O, that would be I, and if it's supposed to be %i5, that's going to be I sub 4. Okay, so I'll put that as a normally open contact. I'll start the rung here, and then I will add a coil that will map it to pump motor dot run. Okay, so now this single rung of logic makes the connection between the real world input and the variable that I'm going to use all over my program for pump motor run. And there might be potentially, dozens of different contacts referenced against this variable. What that means is if I change later on the mapping of this variable, maybe it's not really I5, it's I12 or something, or I need to rework the IO, all I have to do is change it in this one location, and all these other locations will not be impacted. I don't have to do any programming changes here. I just have to change a few rungs in my input side of things, or maybe a few rungs in the output side of things. So in the output, what we're going to do, you know what? I used the wrong variable here, didn't I? I did. Okay, so this wasn't supposed to be pump motor run, dummy. This is supposed to be pump motor stop. It's the stop push button. There you go. That's better. Okay, so on the input side of thing, input 5 is correlated to the pump motor stop push button. When I get to the output side of things, the internal variable for pump motor, let's spell it right, dot run is going to be, that's the internal variable. It's going to be mapped to a real world output coil, let's say Q1. Okay, so percent Q1 would correlate to Q sub 0. All right, so that's the technique you can use to map real world IO into a variable that is arrayed, for instance. And you can use that technique for any variable. It doesn't have to be a structured variable. It can be a regular old variable. And then again, the benefit of that is when you do that, any changes in input or output mapping can be done with simple changes in one area, and all the dozens of other places that utilize those internal variables can remain unchanged. Okay, so hopefully you understand the benefit of that, and you can see the approach that we can take for doing the real world IO mapping to a structured variable. Okay, so we've created a new structure. All right, we created that new structure and we called it motor. We created a new variable called pump underscore motor that referenced that structure, used it as its type. We've picked some of the variables from pump underscore motor. We've mapped real world inputs to some of the variables. We've taken some of the other variables, mapped them to real world outputs. The rest of them will remain internal because that's what they are. Now let's go ahead and just go ahead and program a timer, because a timer also uses structured variables as well. Okay? All right, so what I'm going to do then is I'm going to go ahead and time the pump motor run signal. So I'm going to get a contact. All right, and again, pump motor dot run. All right, so I'm creating a new rung here. I'll drop a timer next to it. All right, and now it's asking for the timer address. Now I haven't created any kind of variable for the timer yet, so I'm going to do that on the fly. So let's create a variable called pump motor timer. All right. Now, for me, a 16-bit accumulator is just fine, and you'll notice Seascape is flagging the fact that this is a structured variable that it's looking for. All right. So since I'm just creating this on the fly, I'll hit the right arrow key here, and now the check mark. I'll double check to make sure this is all correct. So this is the name I want to give it here. It is of the type timer counter 16. That's what I'm looking for. Everything else here is fine. I'll say yes. All right, 100 milliseconds is good. For the preset, I could enter in another variable. I'm just going to make it a set 5-second set point for the timer. Okay, so I've created a new timer called pump underscore motor underscore timer. That is a new arrayed variable. And if I want to access the accumulator, I'm going to access the .acc element. Okay, that's the accumulator for all my timers. And if I want to access a done bit or an active bit, I have the ability, if I want to access the flags part of that particular structure. Okay, so why don't we do this? Why don't we go ahead and show how we might display the accumulator on the screen, and then maybe when this timer expires, the function in the machine is that the pump is ready or something. So let's show how we could also display a pilot light that would turn on when the pump timer has effectively expired. Let's go ahead and do that. Okay, so I'm going to go ahead and go to the HMI section of Seascape, the graphics editor. Let's start with the accumulator. So I'm just going to take a data field object, put it on the screen. All right. Now when I pick my variable, I'm going to browse for the variable. Remember, I just created a variable. It's not the pump motor variable. I just created pump motor timer. Okay, so let's go ahead and select the accumulator for that. 16 bits is fine. We want to display it in tenths of a second. All right. All right, it's a read-only variable, so we don't need anything there. Legend can just be pump timer. All right, we'll go ahead and make the font a little bigger and say okay. All right, so oops, we probably should have made the font even bigger, but you can see what I'm doing here. All right, so now we're displaying the accumulator for that pump timer I just created, all right, by using or accessing the .acc portion of the pump timer. Well, let's create now a pilot light that will turn on, that is tied to the done bit in the timer. All right, and we'll say it means that it's ready. All right, so let's go ahead and again, let's select our timer. This time though, we need to select flags, not accumulator. All right. Now, there's one extra step. Since it's the done bit we're interested in, we have to add the specific bit that means done. Okay, so that would be .16. There we go. Yeah. Okay, 16. There we go. So pump underscore motor underscore timer dot flags dot 16. Okay, so that's what would be after there. All right, and then the legend would be it's ready. All right. Okay. And I may have mixed and matched a couple of different variables there, but you get my drift. Okay, so we can access the accumulator here, and we can access the done bit here. Now keep in mind, when you're talking timers and counters, there's no requirement to utilize the ready bit or the done bit at all. For the done bit, I could have just dropped a coil here, all right, and created a brand new variable that says pump underscore ready or something. Okay, I don't even have to use the done bit if I don't want to. But since it's there, I wanted to show you how you can use it. Okay, so I think that is pretty much what I wanted to show you today. So again, to recap, we've created a structure. We've created a variable that accesses that structure. We've accessed that variable in our program. We've shown you how to map elements of that variable to a real-world input. Similarly, how to map other elements to a real-world output if you need to, and then how to access some of the information from the screen or from elsewhere in your program. Let's go ahead and bring in Casey again. All right, Mr. Casey, so any thoughts, any comments or questions on structures?
Well, I've got my audio this time, so that's always
It is a good start.
No comments or questions, it looks like, that we've got coming in. I think everybody's just ready to create their own structures and give it a go.
Absolutely. Certainly that, I think they'll find that structures are a very useful feature. And really what I like about them as much as anything is they really help you keep your program organized, and it makes it a lot easier. If you name your variables carefully, okay, it makes it a lot easier to keep your program organized and to select the right variable when you're filling out your program, for sure.
Absolutely, the correlation is there, and that makes it easier just for quick reference.
Absolutely, it makes it a lot easier to make very verbose and easy to understand variable names. Okay, all right, so let's not forget that next week our topic is logic simulation for IEC 61131. So a feature that has been much anticipated for some time is the ability to simulate your logic within Seascape. Now, the first logic language that actually has received that feature is our IEC 61131 option, which was added with Service Pack 4. Now, in the future, we will also be adding simulation for advanced ladder with tags as well, but we're not there yet. So I'm sure there'll be lots of folks really interested in checking out next week's topic, where we demonstrate for them how to use simulation when you're using the Seascape IEC 61131 logic programming option. And then of course, every week we have our weekly live streams every Tuesday at 2. Our July schedule will be coming up soon. We'll be announcing that with our July newsletter, or check our website. Of course, we're not done with June yet. Don't forget about the topic for next week. And so once again, I just want to thank you all for joining us and encourage you to try that tag-based programming. Even if you're a dyed-in-the-wool register-based guy, give it a shot. See if some of the additional features are things that you like and you can take advantage of. We think that you'll have a tremendous number of additional tools that'll help and make your life easier as a control programmer. Once again, thanks for joining us, and we look forward to seeing you next week.